Okay, first, so I don't know about you, but I've had just an incredibly good time today. So much so that I suggest that in another 70 years we all get together and do it again. Yes. Oh, my joke didn't get recorded. That's so sad.
You have to do it again.
Yeah. Okay. First of all, at a very, very serious level, I just want you to know how much I appreciated this day. The fact that so many of my friends and so many of my students and so many of my former students took time out of your busy lives to come here and be with me. It's very touching and very moving, and I just cannot tell you how much I appreciate everything that you have done to make this day special for me. I also want to thank the people who arranged this. Ksenia, as much as possible, kept me in the background. So I don't know I don't know for sure who exactly did what. I certainly thank Ksenia, Ibrahim, and Jeff. I know that the three of you put huge amounts of time into this, and all of the other people who I don't know, I thank you once again for putting this together. I guess it was Jonathan who said that it's like a six-sided die and that my thoughts jump around. So for the next several minutes, my thoughts are going to jump around. And I'm just going to pick up on a few topics that came up today. So my wife, Diane, is not a scientist, and she made it through 80% of this meeting. That is quite incredible. Diane's favorite TV show is Big Bang Theory, and part of this, I think, was sociology. She wanted to be here to confirm that we really are just like the people on Big Bang Theory. Now, in fact, I sort of, at times I even try to emulate the people on Big Bang Theory. And you know, the research group there has a Sheldon Cooper. My Rochester group has a Jerry Cooper. So we're following along that pathway. No, time for a Jerry Cooper joke. So my first few years in Ottawa, I don't know why, but I was gaining weight. And after a few years, it was getting to be, wasn't happy with what I looked like. So then I went on a pretty serious diet, and I lost 15 pounds. I walked into the laboratory in Rochester. I said, Jerry, look, I've lost 15 pounds. And Jerry says to me, oh, Bob, I'm so sorry. Have you been sick? Let's see. So it was mentioned that I held a Diwali party a few years back, and that for the Diwali party, I told a story about Mahabharata. Now, the Indians who are in the audience here were polite enough not to point out that I had my two epics mixed up, which I knew at the time. It's just that I didn't know the story of Ramayana well enough to tell it in public. And nobody else, none of the Canadians knew, none of the Americans knew, and the Indians were polite, so everything worked out just fine. But I did know, by the way. I just want you to know that I did know. Now, we heard about nano antennas today a little bit. So, of course, then it's time for a nano antenna joke. There were two nano antennas who got married. The ceremony was just okay, but the reception was incredibly good. Among my other attributes as an educator, I have this long history of turning engineers into physicists. Now, this is not that I don't respect engineering, but deep down, I think deep down inside, I'm a physicist. So when an engineer joins my group, I say, I respect engineering. You're very welcome to work on engineering. I give them an engineering project, and 3 or 4 months later, they say, but the physics is so much more exciting. I say, well, yeah, that's the point. If you ask nicely, I will allow you to change topics. Sean Bentley. Sean periodically goes through a transformation of looking different, grows a beard, gets rid of his beard. So when he walked in here today, I had to turn his name tag over to see who he was. And he said, oh, that's okay. Even when I was your student in Rochester, you could never remember my name. Phase anomaly that Garrett just talked to us about. When Paul Narum had first joined my group as my first postdoc, just telling him about the sorts of things that I was working on, I handed him my phase anomaly paper. He said, that's very, very interesting. He went home and worked on it and said, you know what? You did it geometrical optics, but I've discovered that if you set this up as a Fresnel integral, you can do it more accurately. Of course, that is what GUI had done. But Paul, to his credit, did not copy GUI's paper. He took my paper and decided to do the calculation properly. What else have I not said yet? A serious point. One could mistakenly think that this is my retirement party. I assure you it is not. When I interviewed here in Ottawa 8 years ago, well, anybody who'd interview asked, what are the retirement benefits? They're not supposed to ask my age. So they said, oh, are you thinking of retiring soon? And I said in complete honesty, in 25 years we'll talk about it. Okay, so I have, in 17 years I will start thinking about it. Incidentally, I am very actively working right now on the 4th edition of my Nonlinear Optics book. So I have a commitment to myself to get that book finished by Christmas of this year. So I mean, most of the corrections are done. But gee, if I'm going to be working as a professor for another 17 years, maybe there will be a 5th edition. You never really know. Let's see. Oh yeah, so I think I'll be going for another 17 years. That would put me at an age of 85 or 87. Professor Towns wrote his last serious paper at the age of 98. So, well, of course, I admire him, I look up to him, I try to emulate him, but let's say that if I retire at 87, that's not what I want. I want to keep going. Why? It's a privilege to do physics. It's a privilege to be a physicist. And why in the world would you want to drop out of doing the most exciting thing in the world that you can possibly do? So I mean, that's me inside telling you what some of my future plans are. And I guess that's about it. So let me move on to the scientific part of my presentation. I'll remark that this is pretty much the same talk I gave at the Emma Wolf Memorial Service back in August. So I thank all of you for giving me the opportunity to give this talk while I'm still alive. Of course, he made it into his 90s, so the same career path that I'm on. Okay, so the title is Epsilon Near Zero Materials, How Light Behaves When the Refractive Index Vanishes. You understand now. Enough of you have talked about ENZ that you know where this thought is heading. I've actually changed my mind. If you want a copy of the presentation, I will send it to you. This is not a public talk, right? So I'm not going to post this with my other conference presentations. Okay, so I hope you can hear. I want to stand here. So let me just remind you a little bit about the physics of epsilon zero materials. Epsilon. Dielectric permittivity. So we're talking about what happens when the dielectric permittivity approaches zero. You'll recall that the refractive index is the square root of epsilon times mu. Let's hold mu equal to 1 for a present discussion. Of course, then, when epsilon approaches 0, the refractive index approaches 0. And of course, the speed of light is c over n. The wavelength inside a material is the vacuum wavelength divided by n. What this means is that as n approaches 0, the wavelength is stretched in the limit, becoming infinitely long, and the phase velocity becomes infinite. So it's a very strange type of light. It is oscillating 10 to the 15th times per second, but every atom in the sample sees the same oscillating field. There is no sense of propagation within the medium itself. So that's the first thing of some interest. Second is that radiative processes are strongly modified in ENZ materials. The Einstein A coefficient, I hope in this audience I don't have to tell you what the A coefficient is. But for the dark presentation I did. It turns out that, of course, Einstein first derived the Einstein A coefficient, but Peter Maloney, who's in the audience here, has shown us how to calculate the Einstein A coefficient for an atom embedded in a dielectric material, and you find that the A coefficient is given by the vacuum A coefficient times the refractive index. That means we can control and in this sense inhibit spontaneous emission in an ENZ material. What about the Einstein B coefficient? Well, the B coefficient is the vacuum B coefficient divided by n squared. So this is so strange. Spontaneous emission doesn't happen, but if it does happen, the amplification that it sees will be very, very large. Every atom in the sample sees the same oscillating field. This sort of tells me that maybe superradiance effects are going to be very, very exciting and very, very important in these ENZ materials. And that's a thought that we are actively working on within my, my research group. Professor Ngeta. I failed to mention, although the name is there, Nader Ngeta pretty much invented this research field. This paper of his, if not the first mention of the thought of ENZ, is really what started this field going. So, I mean, I was enormously intrigued by ENZ, wanted to work on it, but you also need something to do. You can't just say, I'm going to read Nader's paper and write the same paper 3 years later. You have to have an idea of what you want to do. So let me pursue that thought a little bit. Okay, so here are some more intriguing aspects of ENZ materials. Well, here's Snell's law, and let's apply it to an interface between n equals 0 and n equals 1, and you see that light always leaves an ENZ material perpendicular to the surface. Now, by reversibility of light rays, that tells you that, well, so now let's ask then what happens if we try to get light to leave an ENZ material. You see that there's no solution to Snell's law for an output direction. That means you have total internal reflection. All of the light is bounded. Within the unity refractive index material. It cannot enter. It can enter only at normal incidence. Now, Snell's law allows for any direction of propagation inside the ENZ material, and then you ask, well, what direction does it really go in? Well, geometrical optics fails us here, because geometric optics says it could be in any direction. So we have to do a wave optics simulation. So here is a beam of light entering an ENZ material, and what you see is that the light actually is emitted in all directions in this material. You ask, well, what about here inside the material? Remember, the wavelength is infinite, so there is no oscillation of the field inside the ENZ material, and I thank Orad, who performed this numerical calculation. Here are some other consequences of ENZ behavior. You can have very funny lenses. So the light always leaves perpendicular to the surface, so the wave fronts always have this form here. If you curve the surface, you will have perfect focusing of this light. A practical implication is that large area surface emitting lasers will always be single transverse mode. What do I mean here? If you want to increase the power that is emitted by a diode laser, you say, well, I'll just make the facet larger, then more power will come out of it. But once the facet becomes larger than lambda by lambda, the diode chip becomes overmoded. And usually it emits into many modes. So you get a messy beam coming out. But if the wavelength is infinite, then no matter how big the facet size is, you still get a single mode leaving the laser. There's no Fabry-Perot interference. There's no phase accumulation in going through a material. What are some other properties? Well, there's something called supercoupling. Now, remember how hard it was the first time you ever tried to couple light into a single mode fiber? I mean, it's really tricky. So then, but then Nader came up with this idea of supercoupling. So let's say you have this region of space, ENZ material, metal cladding around the outside, light enters here, the only place it can leave is here. And it can only leave perpendicular to the surface. So with entirely insensitive to alignment issues, you have coupled the light from this waveguide to this waveguide. You have large evanescent tails for waveguide coupling. This is one that we are particularly interested in working on right now. In fact, I'm so sorry. If we weren't having a birthday party right now, my students would be in the lab doing this measurement right now. So there's automatic phase matching of nonlinear optical processes. Remember that the wave vector magnitude is n omega over c, but if n is equal to 0, the wave vector magnitude vanishes. So that means phase matching is always automatically satisfied. 0 plus 0 equals 0 plus 0. So you even have processes like this. The two input photons are going this way, two output photons are going this way. This would be perfectly phase matched in an ENZ material. Here are some here's some of the intellectually intriguing aspects of epsilon near 0 that that we are either working on within our group, or this is on our list of things to do within our group. So how is the theory of self-focusing modified? Why is this an issue? Well, the wavelength is infinite. So diffraction is always down in self-focusing. Because of that, we're not even sure that the usual Z-scan process works, or that the analysis works. So, heaven forbid, maybe all the data we publish in our science paper is wrong, because we were using standard Z-scan theory to analyze our data. What about the theory of blackbody radiation? I think that Eric's worked on this himself. Blackbody radiation, it's h bar omega times the times the Planck factor or the Boltzmann factor times the density of modes. But the density of modes depends on the refractive index. And if the refractive index were literally 0, there are no modes. So you might just plain turn off blackbody radiation. We have to work through the details. Do we expect strong superradiance effects? I mentioned this already. More generally, how is any nonlinear optical process modified when n0 equals 0? When I'm bored in the evening, I go through my book, and I look at every equation, and I set the background index to 0, and I see what intriguing aspects, what intriguing attributes the process might acquire. Okay. This sounds wonderful, but how in the world do you get an epsilon near 0 material? Do they grow off trees? How do you get them? So there are two major approaches. One is to use metamaterials to design a material from the bottom up that will show this behavior. That's hard. The easier thing to do is go hunting for a material that exists in nature that shows at epsilon near 0 behavior. And any metal or any material with an appreciable concentration of free electrons will be described by the Drude formula. And if you just look at the Drude formula, set the real part of epsilon equal to 0, you'll find that this is the frequency at which epsilon is equal to 0. So any metal will show epsilon near 0 behavior. Now the noble metals, gold and silver, as I think we know, the plasma frequency is up in the ultraviolet. So presumably this will work fine, except that many of the applications we would have in mind might be in telecom. So you want to find materials that have a plasma frequency in the near infrared. So you want doped semiconductors. You want something that has a much lower concentration than in a typical metal. In our work, we have been using indium tin oxide, although other materials have also been used for this purpose. Okay. Now, I mentioned that that's all well and good, but what is our group? I mean, how can we contribute to this? Well, what can our contribution be? So we started thinking about this from the point of view of nonlinear optics. Oh, and I think Orad said this already, that the relationship between N2 and chi3 is given by this formula here. So under epsilon near 0 conditions, you would expect there to be a very, very large enhancement of the N2 value. And I think Orad showed you this already as well, that Israel, Zahir and I did the experiment, and we found that there is in fact a huge, huge enhancement of the nonlinear optical response once you tune to the epsilon near 0 wavelength. Now, luckily for me, I'm not the only person in the world who thinks this is exciting. My friends, Nader, Eric Mazur, Alan Wilner, and I were able to convince DARPA that this was really exciting. And we have just started a multi-year program in developing applications of epsilon near 0 materials for getting a huge nonlinear optical response out of materials. And I won't go through the details here. This is what is called a quad chart. So when you get money in the US, you prepare one of these charts and you send it to the Department of Defense, and if they like it, they send you huge amounts of money in return. So this has been said many times, but now you hear it from me. The students are extremely important to me, both at a personal level, that I help young people to get established in their careers, and also the students are the ones who really get excited, and we do the work together. So this is my, when you have a large group, the photograph is always out of date. So this is the Ottawa group, and this is my Rochester group, and I thank everybody in each group for all of the support that you've given me. And that's it, and thank you so much.
Any questions to Dr. Boyd now? Please.
Jeff, yes.
I've not heard you mention Euclidean extinction theorem.
Correct. I didn't say Avold's extinction theorem. Why should I have?
Well, that is my question. Why doesn't it come up?
In E and Z.
For any of the contexts of your research. Is it just sitting in the background still relevant? Or should one be looking at it and re-examining its relevance? Joining the approximation.
I love the Avold extinction theorem. In some ways, philosophically, you can say, I believe in the refractive index, and I will use that to describe propagation. Or you can say, I'm going to look at every individual atom in this material, look at the field that it re-radiates, and interfere them in the far field. The fact that Avold did it means I don't have to.
So it's sitting in the background still relevant. There's nothing disturbing that's relevant.
I don't think so. But you've made me think. You've made me think. Maybe with maybe under E and Z material conditions, this has to be rethought. I will think, but I doubt. I really don't think that anything is going to have to be deeply rethought. Now, I remember the question you're supposed to ask me. Okay. So, I mean, many of you came a long, long ways to be here, and I would love to, I'm talking about my former students, but everybody really. I'm talking about my former students. I would love to have a chance to get together with you and talk science. And I have set aside my tomorrow, my Saturday. So if anybody would like to get together in my office, it'll be like open house. So anybody who wants to do that, just come on by and we'll talk. And we won't do appointments or anything like that. But at the reception this evening, if you think you want to do that, let me know. And if nothing else, I'll give you my phone number. Because on the weekends, you can't get into the building without somebody to let you in.